In this video, we're going to discuss how to perform a rotation on a material element which happens to be in the surface or on the surface of a pressure vessel. So what we're going to see and this element is that the hoop stress is twice the longitudinal stress as dictated by these arrows here. So sigma y would be twice sigma x in this case. And then we're going to rotate this element by about 45 degrees, and we want to figure out what the resulting state of stress will be, at least for the shear stress. We'll actually also do the calculation for the new um, sigma x prime. But let's go ahead and get started and further clarify that we're not using the standard geometric transformation equations. We're not using Moore's circle. We're going straight to what we know with equilibrium and using method of sections or slicing. So here is a triangle where we have a small angle up top, and we're going to say that this face over here might be this face of the original material element. This face right here would be a portion of this face down here. Okay, this slice actually doesn't necessarily need to be this entire face here. It could be a portion of it as well. And we're going to describe what its actual area is in just a few seconds. The angle is theta, and that would be 45 degrees. But as we've discussed in class, it is wise to use an exaggerated set of angles. In other words, even though it's 45 degrees, namely the angle of rotation, we're going to say it's significantly less so that we can keep track of the trigonometric um, calculations that we're using with sine and cosine. Okay, so this is the sigma x, right? That's the same sigma x coming out the left side there. This is the sigma y coming out the bottom. Notice these stresses are the same as what we have with sigma x and sigma y here, independent of whatever size area that we might be keeping for an element. Really, these elements are infinitesimally small, but we're going to say that they do have some described dimensions in just a minute. The y prime direction, okay, will be parallel to this sliced face. The y will be vertical as it was over here. The tau x prime y prime is going to line up with the y prime. The x prime is going to line up with our new sigma x prime. There's going to be this angle of rotation, theta, which is the same as this angle inside the triangle. This face right here, this orangish face that's at an angle, we're going to give it an area of delta A. As we described in class, both of these elements, this element and this element, they have a depth that we don't talk too much about, but if we said that depth was h, for example, then it would be the length of this side times h would be giving us an area. We're going to assign it to be delta A. And this face, this edge is really the hypotenuse of this triangle. So we can look at this shorter side as being delta A times sine theta, right? This is opposite over the or sine is opposite over the hypotenuse. On this face, we have delta A cosine theta, okay? Hypotenuse times cosine theta will give us this vertical face. The components of the sigma x stress can be drawn as we see here. And remember, we need to use vector addition, so we go this direction, following the arrowhead, and then up to get to this head of the sigma x, right? These vectors should not be drawn, in other directions, unless, the head of this pink arrow was maybe to the right or something else. Okay. The component of the sigma x in this green direction, which is parallel to x prime, is going to be sigma x cosine theta, right? This now sigma x is serving as the hypotenuse for this triangle. Over here, we have a component vertical, or not vertical, but angled in the same direction as y prime, and that will be in the same direction as tau x prime y prime, and that component of this stress is sigma x sine theta. On the vertical sigma y, we can break that stress into two components that are aligned with our new y prime and our new x prime. So this component right here on that longer purple vector would be giving us a sigma y cosine theta component, where the small angle is here in this portion of the triangle. Remember, these also have to be right triangles. The angle may not be super 90 degrees as I've drawn it here, okay? But these right triangles have the hypotenuse, and we need to use vector addition in order to get to the hypotenuse, which is the original stress, right? If we break the original stress into two components, both of these components are going to have less magnitude than the original stress did, at least for these small angles. So now we have a sigma y sine theta for this component, which is parallel to x prime, and actually in the opposite direction though. And on this side, yeah, so we have sigma y sine theta and we have sigma y cosine theta. Okay, so that's all of them. So now we're going to go ahead and we're going to sum in the x prime direction, sum the forces in the x prime direction, and also sum the forces in the y prime direction. When we're performing these calculations, we actually do not use equilibrium with the moments. We're just looking at equilibrium with the forces. So we have sigma x prime delta A, that will be this sigma x prime times this delta A. That will give us a force in the x prime direction. We have a sigma x cosine theta, right? That is in the minus x prime direction, so there's a minus there. And that is acting on this delta A cosine theta. And we see this is a force, and this is a force as well. So we're performing equilibrium on forces, not just on the stresses. And we have our sigma y sine theta. Again, this component is in the opposite direction and parallel to x prime, and that's acting on an area. So this is just a stress and a component of the sigma y stress acting on the delta A sine theta face. And we set this equal to 0. So we get sigma x prime when we do the algebra. We're knocking out the delta A's. We get sigma x prime equals sigma x cosine squared theta plus sigma y sine squared theta. And maybe it's a good idea at this point to plug in what sine of 45 degrees it might be. Cosine of 45 degrees, of course, they're the same. We have square root of 2 over 2. And since these are cosine and sine squared, so sine squareds and cosine squareds here, we can say that those are going to be 1/2. So what do we get? We get 1/2 sigma x plus sigma y. For the forces in the y prime direction, so we're now trying to figure out what tau x prime y prime will be. We can say that tau x prime y prime is acting on the delta A face and can be written as such. We have a sigma x sine theta also parallel to y prime acting on the delta A cosine theta phase. So we have plus sigma x because it's acting in the same direction, so positive, positive on the delta A cosine theta face. And we have this sigma y cosine theta component acting in the opposite direction but parallel nonetheless to the y prime. So we're going to do minus sigma y cosine theta, and that's acting on the delta A sine theta. Remember, this is the component of the stress that is parallel to the desired y prime direction, but it's not a force until it's acting on an area. So that's the delta A sine theta. And so when we rearrange things, knocking or crossing out or canceling out the delta A's, we get that tau x prime y prime is going to be equal to sigma y cosine theta sine theta minus sigma x sine theta cosine theta. And I guess I'll just add a little extra prime there. And that ends up being 1/2 times quantity sigma y minus sigma x. Lest we forget what sigma x and sigma y are for a thin-walled cylindrical pressure vessel, we can write sigma x is equal to PR over 2T. That's the longitudinal stress, and then the hoop stress is going to be twice that. So it's just going to be PR over T. Okay? And so if the question asks us to find the magnitude of the shear stress on an element rotated 45 degrees about a radial direction, what do we have? We just plug in this value, 1/2 times quantity sigma y minus sigma x, and we see that we have PR over 2t, we have PR over t. This is just going to be, well, if we have sigma y minus sigma x, that becomes, again, PR over 2t, then times 1/2, so it's going to end up being PR over 4t. Now, let's do a little bit of thinking though, and it was nice that I had a question from one of the members of the class that was questioning how is it that we went from a state of only having normal stresses to suddenly having this shear stress appearing. And we have sigma x prime as well, but here's the shear stress. And it turns out we didn't do this equilibrium calculation, but we have a sigma y prime, and for 45 degrees, the sigma x prime and the sigma y prime for this particular scenario, those stresses are going to be equal. And we can do more calculations later and look at more circle later to kind of physically explain this in different ways or mathematically explain it in different ways. But there's this sudden emergence of a tau x prime y prime. And so that might be a little bit disturbing. And one way to think about it is, well, equilibrium tells us this has to emerge. Okay, that's fine. But is there a more or another elegant way to describe how this shear stress might emerge? So let's do a little bit of a thought experiment. We have a here like a square, but it's been already rotated 45 degrees, similar to what we are looking for ultimately. Nonetheless, if I had that square, so like just imagine I drew that square at 45 degrees, a diamond, okay? But the sigma y is still acting in this direction, and the sigma x is still acting in that direction. And so just redrawing it with, well, actually, it was kind of cool that PowerPoint like took my drawing and I selected it and said, hey, do you want to make it like smart figure, I guess, or something like that. But you see what it looks like. It's more or less a square, and it's rotated 45 degrees. If I apply this stress field, like we see twice up and down and one left and right, what do you think is going to happen? We're going to be stretching this diamond such that it's going to go kind of more uh, uh, acute in the top and the bottom corners and a little bit more obtuse in the left and right corners. Okay? And so just kind of drawing this and thinking about this. in terms of, what the drawing that you put on a material like a rubber sheet would be doing. And if we go back to how we first described shear strain, notice that, if you started with a square type of figure, and then we apply some shear strain, or we're measuring some type of shear strain, it gets these angles in the parallelogram get distorted. And the shear strain is this angle up here. And we also said um, more rigorous treatment would look at it more as gamma over 2 and a gamma over 2, and then you have this acute angle in this left corner. Okay, and this is the result of pure shear. Now, we do not necessarily have pure shear because we have some shear stresses, while we also have some normal stresses, sigma x prime and sigma y prime. Nonetheless, we can see what's happening here with these angles, and in fact, this element is shearing, and it's been rotated 45 degrees. Okay, so if we, were to kind of look at these angles, we could say, oh, maybe that's gamma over 2 or gamma 2. This is not a perfect one-to-one. If this was pure shear, we could say that we had the shear stress equal to G gamma, right? Remember that? But this is not that case. But just, I'm just going to put a caveat for pure shear. Okay. We remember that we had this. Okay. This is not our case. Okay. But it gives us this idea that, oh, we can develop a shear stress when we observe a shear strain. And the amount of shear strain we're going to have is going to be dependent on um, how soft, how hard the material might be. And that would be dependent on the elastic modulus, on the shear modulus, on the Poisson's ratio, right? Because we also know for an isotropic material that the shear modulus can be given as E over quantity 2 times quantity 1 plus nu. So this is just kind of another way to begin to think about how the transformation of an element reflects the changes and the stresses and the strains that you can have um, in an equivalent state of stress. It's an equivalent state of stress, right? Because the tensor is preserving its information, but the magnitudes and of these new stresses in different directions are going to be different as we rotate. Okay. Well, I hope this video is helpful in understanding how we can visualize what's happening when we rotate an element and its effects on stresses.